Okay, problem number 4. The weight of passengers on a roller coaster increases by 50% as the car goes through a dip with a 30-meter radius of curvature. What is the car speed at the bottom of the dip? So I drew our diagram already. You know, we have a roller coaster with a curvature. What is the car speed at the bottom of the dip? That's all we care about. So the car is going to be positioned here at the bottom of the dip. And we're given a radius, which just means that the radius of this curve is 30 meters. It's already in SI units, so we don't need to convert. And it's saying that the weight of the passengers on the roller coaster increases by 50%. So that means that their weight is going to be 50% more. So if their weight is 100,
power.
If their weight is 100, 50% more is just going to be 50% of 100, which is 50. So now their total weight is going to be 150, 50% more than the original, which is just going to be 1.5, right? If you multiply 100 by 1.5, you'll get 150. Hopefully that makes sense. I don't know why that was so hard for me to grasp. Yeah, I don't know why that was so hard for me to grasp. Okay, and then when it's saying that the weight of the passengers on the roller coaster increases by 50%, they're saying that the gravitational force increases by 50%, not their actual weight. The gravitational force increases by 50%, which I didn't know. Which I guess makes sense because, like, your mass itself can't change. Like, if your weight is changing, your mass itself can't change, right? It has to be the gravity that's changing. And so we know the equation for weight is W equals mg, right? So again, we're saying that the gravitational force that they're experiencing is 50% more. So our new equation is going to be m times 1.5 g's. So from here to here, this gravitational force is some number. This gravitational force is 50% more. When you calculate this, your weight is going to be 50% more as well. We're not actually multiplying the weight by 1.5 here. Okay, so now let's talk about forces, right? At the bottom here, what forces are acting upon the car? We have the force of gravity and the normal force. What is the normal force here? The normal force here is actually the seat of the roller coaster pushing upwards, right? Because the force of gravity is pulling down. It's pulling the roller coaster down. Why is the roller coaster not just like straight falling down? Why are you not falling through? Because the seat that's inside the roller coaster, you're here, this is your seat, this is the roller coaster, right? Force of gravity is pulling this down, but the surface of the seat is pushing up, which is why you're not going down. Again, I know it's kind of hard to conceptualize, but you know, the more you stare at it, the more you think about it, it does make sense. And remember, we are going in a circle. We're at a curve, so there's got to be some centripetal force here, you know, keeping us in this circle. And remember, centripetal force is always directed towards the center. So I know here that the normal force is providing the centripetal force. Okay? Let's also remember that normal force is always perpendicular to your surface. So if your car is here, what do you have? You have the force of gravity pulling you down. Here's your seat, right? So the normal force is going to be perpendicular to the surface. So So your normal force is going to be pointing here. At this point in time, your normal force is, again, it's providing the centripetal force. It's always going to be providing centripetal force because it's pointed towards the middle. And you have the force of gravity pointing down, right? So there is no normal force pointing up, which is why you end up going down, because you have nothing counteracting gravity here. There is no normal force pointing up. The normal force, again, is perpendicular to the surface. The surface is here, perpendicular is here. There's no upward normal force, which is why you're actually going down. If your car were here, again, your normal force is going to be perpendicular to the surface, and it's always going to be pointed towards the middle, so we know that the normal force is actually providing that centripetal force, right? The force between your seat, the force that's pushing up from your seat onto you is allowing us to move in that circle. So we know that our normal force is equal to our centripetal force, and what are we looking for? We're looking for the speed at the bottom of the dip. Okay, so the centripetal force, well, we should know this equation by now, is your mass velocity squared over your radius, right? And again, we said here, your centripetal force is pointed upwards, gravity is pointing downwards. You're not moving up and you're not moving down, so these have to be equal to each other as well. Right? But remember, our force of gravity here, m times acceleration, m times g, is 1.5 times that of gravity. So Fn is going to be equal to not m times g, but n times 1.5 g. And remember, our centripetal force is equal to our normal force. So here, we can set these two equations equal to each other. And what are we solving for? We're solving for, the speed. What is the speed here? What is our velocity? So with some algebra, we multiply by r. Divide by m. Then we take the square root. Hopefully my leg is not blocking. Right, because we're going to have v squared equals this, so let's just go ahead and take the square root. And since we have m here and m here, again, like the last time, these cancel out. So we're just left with the square root of 1.5 g times r. And we actually know all these values, right? We know gravity is going to be 9.8. Remember, we said it's going to be 50% that of the force of gravity. So by having this 1.5 here, we're providing that 50% more than the force of gravity. Times the radius, which is 30. And if you work this out on your calculator, you get 21 what? Meters per second, because we're velocity. And that's the answer, 21 meters per second. Hopefully that makes sense. Quick note, because this revelation kind of just came to mind. On the roller coaster problem, when I was saying, where is the normal force coming from, right? When I said, where is the normal force coming from? And how I said that it's actually your seat pushing up against you, right? At this point, the normal force is here. The normal force, I'm saying, is being provided by your seat, which is why you're not falling down. And it actually makes sense, because let's think about if our car were here, right? Remember, your seat is here. The normal force is perpendicular. So it's still providing that centripetal force. And the force of gravity is pulling you down. Why are you not falling straight down? Seat belt. If you didn't have a seat belt, and your roller coaster is here, right? The roller coaster is going down, you would, boom, fall out of your seat. Because the normal force is not pointed up. It's not counteracting gravity. It's actually providing the centripetal force only. Here, yes, this is pulling up, which is why you're not falling down. But here, the normal force, there is no upward normal force. And you're here. So you would be falling down, but you have a seatbelt on, which is why you're like that. So I guess here it does make sense to say, I don't know if to you it didn't make sense, because like I knew the answer was, the seat of the roller coaster is pushing upward on you, but in my head it didn't make sense. But I guess if you think about it here, it does make sense. There's no upward normal force. You technically are falling down, but you have that seatbelt holding you in place.